Okay, so we'll get started. I sent a message as to what the agenda is going to be. That's what, and I also put up the slides that we are using for today. I assume last week that you remembered are aware of MDPRL. I'll assume even more so this week, because I actually also told you, if you have forgotten or if you don't have the background, there are places where, like my previous lectures, are something that you could read. If you don't, then that's tough luck. Okay. So for the as I said, so let's just start with the grading matters that I actually sent a message about the semester project. As of now, you guys have done 4 homeworks on PDDL domains, planning algorithms, planning graphs, and human-aware planning. There is likely to be one more on RL and MDP. And that would be sort of the end of the homeworks, because these are the pieces where I'm sort of giving the common background for all the other papers. From here onwards, you will go into specific papers that would basically, some of them might be at the state of the art, and there's not anything I can do in terms of asking for homework other than you write the next extended version of that paper. Okay, so that would be the homeworks part. And then there may be a midterm exam, and there may also be paper reviews. I mean, I will give you enough notice if there's a midterm exam as to when it's going to be. It's going to be, there's only one exam, so before the semester is over, it's pretty much the only thing that will happen. And then the paper reviews, there might be in some of the upcoming classes, you may be asked to read and post a review of a paper, one of the papers that we might be discussing during the class. So as I'll say later, one of the things I'm hoping is that part of the class would be to basically read a particular paper and discuss it. Okay, so that you will have a sense of how to read, state-of-the-art papers, because they're not written as textbooks. One of the things as you will have to understand if you are an undergraduate is everything you read in the textbook essentially is a condensed, distilled, or like maybe, the other day somebody was showing on the Reddit how vodka is made. And then it involves like 8 distillations or 15 distillations or something after you kind of make the potatoes go bad. But it's like basically the stuff that shows up in the textbook is like over the time got distilled to almost its essence. At the time this work was being done, nobody knew what will survive the test of the time and what won't. You understand what I'm saying? For example, in your own reasonable lifetime, generative adversarial networks were all the talk of the town, and everybody was thinking that would be the thing. And now nobody talks about it. Now we have moved on to diffusion models. So, textbooks might basically just skip over ideas that aren't particularly working, even though at that particular time they were, taking you to the next level, essentially, because these ideas were in the same. So, reading papers, essentially, you have to realize that that's not distilled at all. It's just a bunch of people who are also at the state of the art reading somebody's submission and saying this is worthwhile presenting to the rest of us. And so it would be quite a different type of skepticism that you need to get when you're reading the paper. You can't just read and take everything as obviously true, because the authors will never say that there's anything wrong in what they're saying. And by the way, you have to understand also that just because something is published even at the top conference doesn't mean that it's actually stood the test of the time already. All that basically means is that 3 reviewers got bamboozled by it, essentially. And this is, I'm not making this up. So this year, there was a huge controversy because this year, there was one of the outstanding papers at ICML, which is like top machine learning conference, was on this security, machine learning security, ML security. And as soon as that paper, it's not just got in, it not only got in, it also became the outstanding paper. And people who were actually, who couldn't be bothered to read the paper as reviewers, because, most people don't want to review papers because that's like doing work for other people. Okay, but they're doing their own work. But after the paper comes out, they look at this and hey, this thing makes no sense. In fact, most of it is wrong. And you would think, how can this happen both at ICML and also an outstanding paper award? You understand what I'm saying? Very much possible, because essentially it's just peer review. That is, people who are sort of, it's like verdict by jury. The jury verdict, as Dave Barry would say, 12 people who didn't know how to get out of jury duty said, what should happen to you? And reviewing, cynically speaking, is 3 people who didn't know how to get out of reviewing read your paper. Okay, they may or may not be the top people. In fact, as an author, you might be hoping that I'll get people who are easily impressed by LaTeX, so that they don't need to know what I wrote. And then once it gets in, it's okay. The only problem is getting in is okay, but if you also become an outstanding paper, then people are going to try to replicate what you're doing. And then you will find if there's actually holes in it, people will find out very easily. Because there's just so many ideas floating about in the world, nobody has time to check whether everything is right or wrong. Truly, okay. The way things get checked is if in fact it's important enough that actually it's working in enough cases, or at least somebody said it's an outstanding paper, then you'll spend time trying to look at whether or not it's working. And then, if it stands that test of time, then it really is good. Anyway, I bring this up just because, some parts of these outside in the later classes will make you read like one paper that just came out recently, for example, and then you will also maybe write a review for that. Okay, those are the things. So this is definitely done. This I'm going to talk about in a minute. These may likely be there as part of the semester evaluation. Okay, and then as far as the projects, I actually put it all up. I don't know that there's any major amount of comments that people had. I just said you can do type 1, which is like a normal semester project. You define the research question related to your own interests in overlapping with what we are discussing here. And you can always convince me that even though it doesn't look like this course, this is interesting enough that I should be allowed to do this. Okay, and so that's the kind of project. Sometimes those kinds of projects actually become papers, conference papers, depending on how good the ideas are. Again, as I said at the end of that thing, that actually coming up with a topic isn't easy. So much of undergraduate life, somebody tells you what to do. Graduate life, you have to decide what to do to some extent, and that becomes harder because, as I said, you could decide not to do anything, so you'll have a lot of good time as a graduate student. You can do a huge amount of world-changing work. And so that's basically learning that initiative is really what you do trying to be a researcher in grad school. And only an epsilon of that might happen in course projects, depending on your level of maturity. So that's one thing. And this I can allow teams, basically, and then it can be probably up to 3, although you can convince me that they can be larger than 3. But that's one type, okay? And then, like I said, there may be a small possibility that we might have project topics based on extending one of our group's recent papers, that maybe one of my RAs might be willing to work with your team. But that, if that's the case, I will announce them. And then if you wind up being interested, you will be. But it may not happen. So it's more likely that you will pick the topic yourself. And then you have to tell me, I think I'll give you a deadline by which you have to tell me what your topic is. The other is type 2, which is essentially, I was kind of breaking my head as to how to make it be interesting enough, where people basically, these are the easier things, you read papers, but one of the worst things is, all of these are partial satisfaction planning problems in the sense that you can do a lousy job very easily, whereas doing a good job understanding papers is actually harder than just doing your own paper. Being a scholar is harder than doing new work sometimes. Okay, so the simplest thing that people tend to do in these kinds of courses is you pick a couple of papers and you write summary. To make it bigger, they'll say pick up to half a dozen papers and write a summary. The problem is you pick the abstracts of the papers and paste in your summary, then it's a summary. And if you think that I might be possibly going to find that you actually cut and pasted, you have access to GPT-3 API. So you put the abstract in there, ask it to rewrite it, and then submit it. Okay. I'm not born yesterday. I know that you should be smart enough to do this sort of stuff. So I was just basically trying to see what would be a more useful thing. And so, but basically what we came up with is you pick 2 papers, sort of this entire course is going to be between planning one side and reinforcement learning MDP on the other side. That's what I'm structuring it as. So you could pick 2 papers, one typically sort of from the planning side and the other typically sort of from the reinforcement learning MDP side, where people tend not to talk to each other. So they would have written those papers as if the other thing doesn't exist. Okay, and so you read these 2 papers, both understand what they're saying and understand what they're missing from each other, what are the things that they could have learned from the other community. It can be like a more interesting, trade-off analysis than just saying that just basically, confining yourself to those two papers. Typically, when you are trying to explain a paper, you need to explain a whole bunch of background material. To even understand a paper, you need to understand a lot of papers that they have referred to, for example. Now the question again is, how do I evaluate whether or not you did this? So you get to these two papers, and in the first stage you tell me what your two papers are and why you think they might have things in common. So that would be like the project proposal stage for this kind of a project. Okay, and then if I think I can see approximately that there is a good reasonable job to be done, I leave it. If not, I might suggest, okay, in this pair, A and B, keep A, but instead of B, get B dash. I might be able to suggest that then, because at least you did part of the work, and then I just need to do a local repair as against coming up with specific pairs of papers. Okay, and then after that, you read the paper, you understand the paper. At the two papers, you try to understand the distinctions and the connections and so on. And then the other question is, are you going to write a paper or give a presentation? We have decided you should do a presentation. Except not in the class, because as I told you, I don't want you to waste other people's time. So what we'll do is you'll record your presentation, put it on YouTube or something. Okay, it can be between 15 to 30 minutes. You make a nice presentation with slides and so on, explaining what you've learned. Okay, and then the question, of course, is who's going to watch the answers? I'm not going to watch huge number of. So what we're going to do is you're going to get 3 of the people from the class, watch each of these projects and write anonymous reviews. You understand what I'm saying? And it would be randomly assigned. Otherwise, I know that all of you will collude and say, whatever, 5 for 5, the Uber thing. Right, so you say my project is good, and I say your project is good. I know how this works. Okay? I've been here for long enough time, right? So it would be anonymous reviews, and furthermore, I will read the anonymous reviews. And the reviews, actually most of my life, I'm like an area chair or a senior program committee member for conferences, and I make my impressions on researchers based on their reviews, because I can see who's writing. It's anonymous to you guys. You will get just 3 people from the paper, from your project, 3 people from your project who have written the reviews. That's how normal conferences work. But I know which are the 3 people who wrote it. And I know how they wrote it. And it looks like, there was this one time I was running Ichikai in 2016, and there was this one particular reviewer essentially said, looks like a great paper, 10 out of 10. And I told this person, in Ichikai, in all the time I've been there was barely like 2 papers which got 10 out of 10. And if it's 10 out of 10, that's like metaphysically great paper. And so you should give a little more than looks great. Okay, write a justification. And then an hour later it became 3 out of 10. I'm not kidding. Okay, you have to understand that reviewing is done by people like you. Right? That's very close to being grad students. Reviewing done by other grad students, mostly. Okay, and so if they don't know, they essentially, everything looks good. And also if you can't understand, you still have to give a number. It will be like America's Got Talent, right? With you not being Simon Cowell, right? So you just give a number and you don't give an explanation. So reviews, you have to give an explanation. So I'll make you actually write conference reviews for this project that you would be doing. And so your grade for the semester project would be based on both your own project, the evaluation of which involves what 3 people else said as well as what I thought, plus your reviewing of other people's projects. You see what I'm saying? With this, I'm hoping that you'll at least learn how the world works. And you would be, instead of, so by the way, the anonymity of reviewing is like taken for granted in computer science. In fact, in computer science, the papers are submitted. I might actually make you do this too. Maybe not, because you are actually doing a presentation. So how can I actually move your face? So people will know who is registering. But so in normal computer science things, they basically make the papers be double blind. That basically means single blind is normal, because if reviewers tell you who they are, they won't be there for the next reviewing cycle. You would have already dodged their house, right? So basically, the reviewers will never tell who they are. And the question, of course, is should the reviewers know who you are? And the interesting thing is that there are all sorts of interesting issues about whether or not knowing the person's name influences your review or not. It actually does. It actually does. But in ways different from what people think, essentially, because the bigger problem is not so much that you would be intimidated by a paper which has Jeff Hinton as the second author and say, what the heck, I'm just a grad student who knows how kind of blind this reviewing is. You might find out that I gave like a low mark for Jeff Hinton's paper, and there goes my research career. That's what you would be thinking, but the real reason, actually, I think temporal planning review is good is because if you get some person, a paper by a name which says Tom Nobody, okay, and working with Jane Nobody, then you'll think, yeah, these people can't write good papers. They're not Jeff Hinton, they can't write good papers. So it can work the opposite way. I don't know these people, how can they be good? You understand what I'm saying? And so, in fact, double-blind reviewing is more important. I have argued for double-blind reviewing in all the places that I've been involved. Not to basically say, not to say that nobody should know whether it's a paper written by Jeff Hinton, because people can kind of figure out capsule networks for more paper, it must be Jeff Hinton. That's what he's doing the last couple of years. Okay, but some other idea which you don't know who might have written, and then there is a name on the top, but you don't recognize that name. If I don't know, it can't be good. So, and that might give you this thing. So that's why actually people do double blind reviewing. But we may not do the double blind part of it. We'll do certainly the single blind. Okay. Yeah. Any questions on this stuff? And I gave some suggestions as to how to pick the papers, and picking two papers from proceedings is not easy. That requires some work on your thing, trying to say you have to kind of figure out what kind of topics in the intersection of your interests and this course are you more likely to look for. Do some Google Scholar search and look for I'll also basically the proceedings papers titles. And then from the titles, by looking at the abstract, you kind of figure out which. So that requires actually, picking the problem is what you learn as a researcher, by the way, not solving the problem. Solving the problem is what you learn as an undergrad. Okay. Basically, you expect to have to spend a bunch of time trying to figure out which two papers to pick. I'm just saying. And imagine that all I can say is it's actually simpler. The only reason I put this in is because the thing that actually matters is the type A project, where you make up an idea and then you follow that. That will be even harder, trying to figure out, what idea should I try? Because most of the time, what idea, basically figuring out what is interesting and what is feasible is something that you get only over a period of time, as you get experience in doing research. And so they will spend even more time if they're especially actually completely new to the research or something. Okay, let's see what's your question, and then I'll get to you. Yes.
Shouldn't there be a conflict of interest declaration before the anonymous reviews? Because let us say I know person X.
No, I understand, but I know, but there's only so much I can do in that particular sense. Okay, but I can read your review, so I can sort of figure out. By the way, the idea that people are trying to defeat this kind of reviewing and collusion cycles, it's become unfortunately true right now. The 545 has become, actually a known problem in some top conferences, where people will pass their paper ID, and then their friends will then bid for that paper ID. And in the old days, we can go into this whole thing about reviewing. So in fact, one interesting thing is that before you can ask 3 reviewers to review a paper, you would like to see whether they would possibly be interested in reviewing that paper. Imagine they are like linguists. Okay, what is the point in making them read a paper on reinforcement? And imagine you are a reinforcement learning person. What's the point in making them read a paper on semiconductor manufacturing? right? You can force them, but they'll just write some random. So one idea used to be that you would take bids from people and then use those bids to kind of assign, who should review what paper. And unfortunately, in a good world, that would work very well, but people are actually using the bidding to defeat the reviewing system. Essentially, they would, send all their friends their numbers, the paper numbers. So you bid for my paper, I bid for your paper, and then some three good people that I know and like would get my paper, and they'll say good things about it. Okay. Again, and part of doing all of this is also to lose some of the mystique about conferences. They are run by people like you. The reviewing is basically done by people like you, the graduate students like you. And so it's a human endeavor. So all you know about conferences is the very best ideas are likely to get through. Very worst ideas are likely to get stopped with high probability. In between stuff is a tougher. It depends on which three are. I mean, most papers in any of the top conferences you can think of could basically, I can get you 3 reviewers from that same conference who either give it a best paper award or would say this should be strongly disputed. You see what I'm saying? So that's just the reality. So in fact, there are all sorts of interesting stories about this in real life. I mean, there was a case where one guy in long back in AAI, he sent a paper. This guy, Johan de Cleer, he sent a paper, got rejected. 1 year later, AAI deadline came along. He has been having too much fun, didn't write any papers. So he looked around to see, do I have any papers already written? This rejected paper was in the drawer. So he took that paper and sent it. This time it got the best paper award. Nothing has changed. It, unlike wine, which does kind of mature in barrels, a paper put in a drawer without you touching it doesn't mature. What matured is essentially the reviewer's change. Okay. The reason I'm saying this is not to make you cynical, but to realize that it's a stochastic process. And as things are becoming much bigger in size, especially some of the the big ML conferences are, there's been this almost a crazy rush towards, we have 8,000 submissions, we have 13,000 submissions, etc., etc. There are people who can read this stuff. People like you, and you say it looks good, and yes.
How did you want us to submit ideas for type 1 projects to you?
I will give those details. So, I think, as I said, by this weekend, I will basically give dates about how to submit proposals, etc. Okay, if there is, my question was, I wanted to wait until this weekend in case people have problems with this setup, because I didn't know. Yeah, you had a question. And then.
So about the review process. So I think in CS, people don't commonly publish with paid journals.
What?
In CS, people don't often publish directly through paid journals like
paid journals. Yeah.
But so do those paid journals kind of avoid this problem? Like, I mean, they have the problems that they don't pay people for their research, but it's all.
No, actually, paid journals are okay. So that's again, this is an interesting side topic about research in general. All journals were paid journals at one point of time. As much as people want to make fun of LCVA and Springer, etc., these guys, if they didn't exist, they would have been new physics. Because there had to be some journals in which it's been published, and somebody is taking time to actually get it reviewed, etc. And those times, those were the private journals that used to do it. Okay. Some journals can be, like right now, things like Nature, for example, are still paid journals, and people would, all the people who say paid journals are bad would change their tune like faster than Ron DeSantis if their paper gets in to Nature. That's what I'm saying. I didn't mean that there's anything wrong with Nature. They take my paper, that's completely fine. You see what I'm saying? So, except that now people have also realized that there's like a racket. So, tons and tons of very, people who just start this as a money-making thing, and that's why the quality gets compromised. But I don't think there is actually journals in general are slow time, and so they are likely to have longer review process. So again, I think it's a useful thing to discuss. The difference between conferences and journals in computer science in particular is actually computer science is pretty much the only crazy area which is into conferences. Nobody else is. No other area is. But since computer science is the only thing, in fact, computer science contains AI and AI is the only thing. So whatever AI does, everybody has to follow, right? So the problem with the good thing about journals is that you submit a paper, they'll send it to 3 reviewers, carefully chosen by the associate editor. And then after they review the reviews, they'll also say, if these things are fixed, then we might reconsider our decision. And then you will be given like a significant amount of time to fix those. And then they will reread the paper, etc., etc. In some areas, actually, there can be 7 such rounds, which basically means from the time you submit the first version of the paper to the time it actually gets published in the journal, it can be many years later. This was actually true for most of its life science actually worked that way. And so people don't have that kind of a, if you don't like, but so either you have the patience to wait, in which case you get better reviews, or you want instant gratification, you submit it to one of these conferences with gazillion papers submitted, all of them would be decided by a particular time. And what's happening is, we know both of these have problems. Journals basically by the time, especially in a fast moving area, by the time the paper comes out, like about 10,000 people have already did other better things than the idea you're saying, and nobody cares anymore. Right? Because the state of the art is moving. And so there's basically, again, as somebody said, what's the half-life period? I mean, you know that an area is fast in terms of the half-life period of interest in the best idea in that area. How long will it stay? And if you start fast-moving idea, that's not going to happen. And so people are actually trying to combine these two things. I mean, conferences try to become more like journals. Journals try to become more like conferences. Everything's a mess. But I don't know if that answers your question at all. But it's not the problems of reviewing. Again, I think there are. I always thought the world has enough resources for a few people to have a great life. The problem with the world is it doesn't have enough resources for all of us to have a good life. And we are not into kind of giving up our life so that other people have slightly better life. And so there's huge amounts of inequality. The same with reviewing. The problem with there are enough, if you decide only like I'm going to review a few papers, you can get them reviewed carefully. And so journals like Nature, essentially they are not journals at all. They are popularity contests where you submit the paper. First, you'll say, I want to submit a paper. You'll say, what's your name? I can't even spell it. No, forget it. Okay. And then you'll say, okay, here's the paper. They look at the paper and say, these are people who are not doing research. They're just looking at the paper and saying, yeah, kind of nice. And say, no, I don't think our readers will be interested in that. And then, so by doing this, essentially, they have cut down to the set of papers, such as AlphaGo or something, which has already kind of everybody knows, and nobody really cares whether or not it is written up in the journal or not. Right? And then they will get it reviewed. And I'm sure everybody would want to review the AlphaGo paper. So there you will get the 3 good reviews. What you want is some random paper that you thought of as part of this course that you want to submit to NeurIPS or ICML or III. They should also be reviewed as well. Yeah, I agree that everybody should have a good life, but there's not enough resources. Not enough reviews. Any other questions? Yeah.
So you said that the type 1 projects will be most useful for PhD students, but you are not restricting or discouraging them from choosing type 2 projects, right?
I'm not doing anything. I'm not stopping anybody. In fact, I was doing I was worried about the opposite too. So I think any of them you can pick what way you can. Anything else? Yeah.
Would this review process apply to both projects or just?
I believe so, but I have to figure that out more. My guess is that there'll be fewer projects and more people thinking that getting 2 papers and somehow depending on GPT-3 make slides. Stable diffusion. I'm telling you, GPT-3 for the bullets, stable diffusion for the graphics. Right. And then anyway, the reviewers themselves will be GPT.
Yes.
How do you know? So I think that's that. Okay.
Never know.
So I'm assuming more of them will be that sort of a thing. So I will just, I mean, it's the problem is I'm not an earnest guy. I'm a cynical guy about the way the world works. And so I wait to be, disabused of my thing that everybody is raring to do projects. So you can always do that. But, I'm just saying that more likely I expect more people to do that. Which is why I spend more time designing those. Because type 1 is just like it's a good project. I'm not like, you get to come up with the idea. Anything else? Yeah.
So regarding the type 1, like it's normal that if we expected it to be more of a, like you said, partially observable kind of thing, like not very specific details as to what is expected or something like that. So that's
For the type 1, you need to first say what the project is, and maybe you have to provide a proposal as to what you are hoping will come out of the project.
right. So is that like,
And then, and then do the project. It may not come out that way.
correct. Yeah, I mean that's the
way. I mean, post projects oftentimes are reasonable. Like you may try to do something, and so in fact, I think I suggested one, which is not. I'm going to say it in the class too, but I suggested one, for example. Like basically, this is not. It's something that falls almost at the intersection of I'm redoing something. Type 1 projects can be I'm going to re-implement some algorithm. That would be okay. Okay, but this one, or you can actually write something that actually changes the world. Okay, but the one that I'm suggesting falls in between, where essentially I was just saying, one of the things that I've been talking in this class is that simulator-based RL essentially is doing planning, except in a different way. Instead of using A-star search, etc., it's doing, it's basically doing Q learning and TD learning, etc. Okay, so the question then is, what are you losing? What are you losing? If in fact, suppose you actually happen to have a PDL model and you convert it into a simulator and you ran, an RL solver on that, and you also ran a normal planner on the PDL model. How bad can the efficiency get? It's a worthwhile thing. People know that it could be bad, but people mostly don't actually try to understand how bad it can be. You see what I'm saying? And this can have all sorts of interesting questions. In fact, imagine the following version where take Locke's word in symbolic PDL model. Generate pictures for the Locke's word. So the initial state is an actual picture, with like hues of the blocks and all that stuff. Okay, and calligraphic A, etc. And then a goal state is a picture. Then all of a sudden you can do deep reinforcement learning. You see what I'm saying? But then the DRL needs a simulator. The simulator basically says, what is your state? What's your action? I'll tell you what the next state is. But that simulator basically can be run by a PDL model, which basically looks at the picture and basically says, okay, this is the symbolic description, computes the new state, converts the new state again back into a picture, and gives it to you. So that you feel it's all in pictures domain, and then you're doing RL. Okay, by the way, Atari games, which have become like the vehicle for deep reinforcement learning research for the longest time, essentially the Atari games, the engines are symbolic in essence, because they do it in some representation, some condensed representation of each of the states. Except they have an ability to convert that what they call RAM state into a picture, because you can only read pictures, you can only see pictures. But then the problem is, when I give you the picture, did you get the same kind of abstractions that the symbolic model already contains? There is no guarantee that you would get the same symbolic abstractions. You see what I'm saying? So interestingly, this problem doesn't come up directly because there are a certain set of domains for which typically people have written symbolic models and they would not even touch RL with a 10-foot pole. And there are other problems for which there are no symbolic models, and RL will just basically use, nobody bothered writing a symbolic model for that, and RL will try to use essentially simulators that I can. Where the simulators, you don't know how the simulator is written. Is it like a piece of code, or is it essentially a PDL domain model that's essentially being simulated. Both are possible. Okay, so the question is, how bad can it be? And in general, one of the things you want to understand in the current AI is universal weak methods, which basically don't make too many assumptions about structure of the problem, will work all the time, but they work with a sucky performance. Okay, and the stronger ones will work better in representations in problems where certain structural assumptions hold. So if in fact the domain could be written as PDL domain, you should have solved it as a planner rather than as an RL. But if you are essentially saying, I have an RL, I'll travel, then you will just take anything, whether it was originally symbolic or not, and try to solve it as a simulator system. And you could do much worse. I mean, this is actually part of the lecture, but you could actually say, I keep saying this, you could actually try to get some kind of a quantitative idea as to how bad this disparity can be. Do you understand what I'm saying? Okay. I mean, and you can actually do this project either with the RL itself being symbolic. That means it actually does have a state, but it just doesn't know what the next state will be. It has to ask the simulator. It doesn't have the action model in front of it. That would be like a CSP solver asking a piece of CSP code, is the partial assignment okay with you? Or unlike like a SAT solver, which basically can directly see, because it has the constraints declaratively represented in front, it can actually directly see whether or not the partial assignment is okay. And that's what PDL planners were doing, because they have the domain model in front of them. They don't have to ask, is this action applicable? They know that the action is applicable. And furthermore, because the action model is out there, they could actually derive heuristics such as the whole planning graph ideas, etc. That could be done. That would be harder to do with the simulator. That's just a symbolic level. And then I throw in like an image in, image out, IO. Then you are in deep reinforcement learning. Right? And the question is, yes, you can do something, but is it really anywhere near close to what the symbolic model would have done? And also, are you learning the correct symbolic abstraction? That's another huge open area. Any other comments, questions? Okay. So the plan for the rest of the semester is that I'm going to say, after today's class, which is basically, I'm going to mostly take your questions on the stuff that you already looked at, and then talk something about, a bit more about RL and planning connections. My idea is to organize the rest of the lectures to jointly present planning and RL approaches for some specific extension at the same time. So for example, it turns out that if things like abstraction are big everywhere, abstraction is important, planning itself is important. Okay, and they have ideas that come from different directions for abstraction. And so we could read like a couple of papers, or I would actually try to kind of give an overview of the kinds of methods in both, so that you can put them next to each other. Similarly, advisability. You want to be able to advise your planner. You also want to be able to advise your reinforcement planner. Whenever I say RL, you should say it sort of like a planner. Okay. So, what are the different approaches that were used? And that's something that we want to look at. Explainability is another thing. Time and duration and partial observability are things that we haven't looked at up until now, but they're actually important. So actions don't have to be instantaneous. They can be durative. And in planning, that's called temporal planning. All planning is really temporal planning, because every action in your life takes time. And the problem is, when action, basically you can no longer do actions sequentially. You might have to do actions concurrently. You do one action which is started and it's going to take a whole bunch of time, and then you do another action in concurrently. So how do you cook? You keep the stuff on, and then you put your thing, your dish on the stove. If you say, I'm only going to do it sequentially, then it's useless, because the stove operation is over. That means now stove has become cold. Then you put the thing, it doesn't help. All interesting problems are concurrent plans. Okay, normal planning, basically you care about parallelism only for efficiency. In temporal planning, concurrency is needed just for feasibility. There is no way of solving certain problems unless you do actions concurrently. For example, a classic example is, you are in Florida and the power got cut off because of Hurricane Ian. You go down to your basement to see if you can do something with the main switch, and then you light a match to look for where the main switch is. The point is that you have to keep the match lit while you are making your way to the main switch, because if the moment it goes off, you don't know where you are. So you have to keep the lit match. While the match is lit, you have to find where the switch is, and then you can try to switch it on and off. That's a concurrent thing. And there, sequential wouldn't have worked like at all. It's not for efficiency, it's for actually feasibility itself. And that's what happens in normal temporal planning. And in MDP parlance, those are called semi-Markov-Decision processes. Because Markov-Decision, the semi-Markov-Decision process, because essentially, once an action takes more than one epoch, it's no longer Markov-Decision process. In fact, one of the things we talk today is Markov is very finicky. Okay, Markov requires that things be dependent only on the current state. And Markov decision processes expect Markov dynamics and Markov reward function. That means the reward dynamics should be completely based on where you are, what state you are in. And when you do an action, the state that you do an action tells you what are the states you get, not how you got to that state. Markov reward basically means when you get into that state, the reward washes over you. It doesn't ask, did you, by the way, visit also this other state or other state? If so, I won't wash you. You see what I'm saying? Sometimes actually you get reward based on the trajectory of states you visited. And there, then the reward function becomes unmarked. You see what I'm saying? So anyway, semi-Markov decision process is one of these non-Markov conditions that you know how to handle, sort of. PAM-DP is the other non-Markov condition we know how to handle, but it's very sad way to handle, which is you take a finite state space and make it into belief states, which becomes a continuous state space. And then I'll talk a little about the rewards, but basically I already told you, like the partial satisfaction planning thing, to actually write it as a Markov reward function, you need to expand the state space by adding an extra state variable. That's because partial satisfaction planning actually is a non-Markov reward. You see what I'm saying? Can anybody understand why partial satisfaction planning, where you can do as many goals of these n goals, and the more you do, more points you get? Why is it upfront non-Markov?
Wouldn't it be dependent on previous states then, because if you're fulfilling partial states?
Yeah, but I mean, exactly why? I mean, I think it's in general sort of true, but why? There is a pretty clean reason why it happens for this. Remember our first idea, which is to make every goal state be having the reward of that goal state, and that just leave it at that. What is the problem with that?
There's no fixed goal state.
There's no fixed goal state then.
No, there's no fixed goal state ever. Reward function basically means there's no fixed goal state. That's something that you have to understand. Yeah.
Did you just revisit the same goal state?
Yes. Yes. How the heck do you figure out whether you revisited the state? That's history. Do you understand what I'm saying? The reason partial satisfaction planning is non-Markov is because if you directly try to use it as a normal reward function, you would essentially should be allowed to go back to the same state many, many times. And you don't want it. For your problem, you don't want it. You don't want it to get the bonus for this goal more than once. Yes, go ahead.
Did you represent the state space differently? Have like the power set of how many of the goal states?
Well, yeah, no, I said a very simple thing. Whatever you're doing, I just said a much simpler version, which is just add an extra variable to the state called dump. That means whatever is the state fluids, add another Boolean variable called dump. And which basically says, no, it's actually, it should be called I am done. Okay, and then the I am done is you say, basically it's like the planner deciding, I've done enough of goal gathering, I now want to get my rewards. And then the rewards are given only for the goals that you have visited by. And in doing so, you essentially double the state space, right? Because you just added an extra state variable. And the reason I say this is actually in deep reinforcement learning, when people are essentially mostly talking about trajectory constraints, like, in fact, as we'll see, most of the examples, even though like RL and planning, I use this word that, I think I said this, Great Britain and America are two great nations separated by the common language, right? In the sense we can't understand what the heck they're saying. I mean, are there any Britishers here? Okay, so, and then they can't understand what the heck they're saying, right? Same thing with RL and planning. They're both solving the same problem, but they can't understand each other. You see what I'm saying? Because of the way they come from different directions. And so in RL, the kinds of instances of the problems they actually look at are typically things like make the robot walk gracefully. Like, what is the goal for walking? What is the goal for walking? I mean, it's like all robots essentially get the robot to the edge of this room, at the corner of this room. That's a goal of achievement. That's not what you mean by saying I learned how to walk. Kids basically walk like this, almost falling up, and we say, either I don't know whether we are laughing at them or with them, but it's hilarious up until they know how to walk properly, right? And they slowly figure out how to walk properly. But the point is, if you are telling your robot, this is not a good way to walk, this is a better way to walk, etc., your goal, or the generalized goal, is a trajectory constraint. You see what I'm saying? It's not any one particular step, it is the way you walked is that. And there are two model robots walk, and you say this model robot walks better. And then the other model robot then needs to learn from this model robot, essentially that you seem to like whatever this other guy is doing. That's a classic non-Markov reward function. You understand what I'm saying? So when they say we learned the reward for that, if you actually started thinking there was an original state space and you tried to learn this reward into that state space, you must have increased the size of the state space. You have to, because otherwise you couldn't have captured it. But nobody talks about this sort of stuff. And you have to ask yourself, why not? Why aren't they talking about it? It's theory. It actually, it is the case that if the rewards are non-Markov, then you have to expand the state space. But then, part of the reason people don't talk about this, in my view, it's probably a cynical take, is that if you start from pixels, you already are sunk. Essentially, they are like infinite number of states in terms of pixel space. Do you understand what I'm saying? Right? Because, you have, pixels, basically, like how many pictures are there? Essentially, it's continuous space. Although you could say they're discrete intensity values, but they're almost essentially a continuous space. If you start with an infinite state space, no problem. It's like the Hilbert model in the sense that it will be, I increase it still. I mean, you already sunk. How can you be sunk anymore? But in essence, they do have to consider changing something in the state space. I mean, there are like two issues that happen in the partial satisfaction plan, right? One is that you actually changed the encoding of the state so that there is some mechanism to keep track of the reward, the history dependent reward. The other is that in doing so, you increase the size of the state space. For MDPs, actually, you do increase because you start from a finite state space, it becomes double the size. You could have trajectory constraints. You could do partial satisfaction planning in partially observable symbolic world. There I said it. It's symbolic world. There are only m Boolean state variables. There are only 2 power n states. But it's partially observable, which basically means it's a POMDP. That means the actual belief space is distributions over these states, which means there are an infinite number of them. And now I'm asking, for partial satisfaction planning on that, not just a single goal. This, I'm screwed anyway. Already lost in space. You understand what I'm saying? You know, one of the things that happens is when you read a paper, you have to ask yourself, what are they not telling me? You understand what I'm saying? It's a lot more important what they are not telling you. In fact, they're not telling you infinite number of things. They told you 9 pages worth of things. There are infinite number of potential things they're not telling you. And as to why people don't bring it up, it's like, you know, it's not that they're necessarily trying to cheat you or anything, you know, it's like, you know, they may not be aware of it, they may not actually understand this will happen. But this understanding for you is useful. It may not be useful in the program level, but it's useful in that, you know, it used to be non-Markov and it became Markov. Actually, I should write this down here. So, with partial satisfaction. Okay, that's part of the reason why, you know, the deep reinforcement people may not be talking about it. Although most of the goals they look at tend to be trajectory goals, because deep reinforcement learning sort of things have been most visual, most visible in robotics, where it is actually pretty hard to write it as a symbolic function. In fact, this was the thing that I was telling you earlier, tacit versus explicit. I mean, in the sense, can you define what a good work is? No, I have no idea. It's like, can you define what obscenity is? And the Supreme Court Judge Oliver Wendell James said, I don't know what an obscenity is, but I know when I see it. Explicit versus tacit knowledge. Obscenity is tacit knowledge, apparently. Right? Do you understand what I'm saying? Graceful walking is tacit knowledge. Everything can be put into tacit knowledge, but certain things you don't even actually have a symbolic description. And in those are the cases where essentially going for it almost as a simulator-based RL, that's pretty much the only game in town in that particular case. I mean, there are trajectory goals in PDL. We will talk a little about that, but not anywhere near as generalized as, you know, what you can do with the generalized reward function. Okay, so yeah, we can also talk about partial observability, and then we might talk about cross-cutting approaches, planning applied to R and vice versa. And you were saying, great hope you have of doing this, because we haven't completed the 4th slide of the. I've actually reduced my ambition and cut it down to only 30 slides, and I was very worried that I will run out of them. So I guess I don't know. Okay. Anyway, MDP review. These are the things you should have understood by now. Okay. If you have things that you haven't understood, let me know, and I'll go over it again. So you should have understood that what the finite horizon value iteration is, and you should know how to convert the finite horizon value iteration to finite horizon as a finite horizon value function to finite horizon policy function. Okay, because if you have states S1 to Sn, then essentially, and you have a horizon H, then you have value functions V1 to VH, actually V0 to VH. V0 is the value function where you have no actions you get at that point of time. Then what is the value? And VH is you have H actions you can still do before you die. And the finite horizon value function, basically value iteration, computes V0 to VH. Each of which are of size S. And then once it computes it, it converts that into, actually in the way it computes it itself, you can convert it into the policy function directly. Is any of this surprising to you? Even if you don't admit, if any of this is surprising, then you're not really doing what I'm asking you to do. Either you should know RL or you should have seen those lectures, because otherwise I have to repeat the entire 4 lectures. Okay. Then the infinite horizon is basically finite horizon from an operational point of view. except, you just basically, the horizon is h equal to infinity. And because h is equal to infinity, then there cannot really be any difference between, the value functions are written as 0 steps to go, h steps to go. For infinite horizon, it's always infinite steps to go. You're never done with, never saying I have no more steps to go. Because of which it's v infinity, v infinity, v infinity, v infinity. And so you just have one value function. And the way you can compute that value function is you act as if it is a finite horizon MDP, V0, V1, V2, V3, V4, V15, V15,000, V15,001, and you say, hey, between 15,000 value function and 15,001 value function, it's two vectors. This is V15,000. It's a vector of values. 0.7, blah, blah. This vector is of size S. And then V15,001 value function is another vector. It's also of the same size. It's also real numbers. If these two vectors are the same, then they're never going to change any further. So it's like planning graph with flattening out, flattening out, reaching the fixed point. Okay, so but two real number vectors never will be equal because real numbers can never be equal. And so instead, what you do is typically you compute a distance function between the value vectors. Normally, the distance function that you compute is the max norm. So you'll say V15,000 minus V15,001 max norm, which is you essentially subtract one from the other vector, take absolute values, take the particular coefficient. Then this difference vector will be of the size S. You take the coefficient that has the highest value. This will be positive. If you drive that down to 0, then they must have become equal. So you keep track of the max norm distance between the vectors between two different iterations. And if it falls below some epsilon that you have decided upfront, then you stop. Then you say this is the V star. And once you do the V star, you know how to convert it to pi star, which is a policy function. Okay. And then these two are, you have to understand these because they're like the bread and butter of the theory of Markov decision processes. In fact, some of the most interesting theoretical parts come from the value and policy iteration. In particular, why do you really believe that as you keep running this value iteration, the max norm will eventually come down to 0, or basically in the limit will approach 0? Because there can be sequences that are divergent. See what I'm saying? But it turns out that, if you looked at the lectures or the textbook, it turns out that the Bellman update, he has this property called the contraction property. So if you update, if you take a value function, and there is an optimal value function V star, you take a value function V1 and V star, let's say max norm is epsilon. Then you applied Bellman update to V1, you get V1 dash, and then take the max norm between V1 dash and V star. Where V star you don't know. I'm just basically oracularly saying, imagine you use the V star. Then contraction property says that this max norm could not have increased. It could only have reduced or remained the same. Which is the proof that value iteration will converge. The beauty, of course, and actually this was something that I was talking, almost there was like a half a class after the class was over last week because two crazy people kept on talking to me about random things. But so I'm going to repeat what happened there, which is, so if you think of value iteration, right? Based on the value iteration, if you ask yourself, how long will it take? Complexity of doing value iteration. When will the value iteration converge? The theorem that I said is it will converge. I didn't say when it will converge. even in the worst case, you have no idea of giving a good bound for value iteration. Actually, the only reasonable bounds people know are exponential bounds. So it would look as if MDP with S number of states will require time exponential in the number of states to compute the policy. If you think value iteration is the only algorithm you know. Agreed? Okay, it's like one of the bread and butter algorithms. But it turns out that MDP optimal policy can also be posed as a linear program. This is a graduate class. I can imagine that you know everything. Okay, so a linear program. How many of you have heard of linear programming? Okay, so linear programming is essentially trying to optimize a continuous objective function defined in terms of some variables, 3x1 plus 5x2 minus 12x3, blah, 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 optimize this, subject to a bunch of linear inequality constraints, saying 12x1 minus 7x3 can never be greater than 4, and 14x1 plus 15x3 minus 13x5 should be less than or equal to 5. These are all the constraints. And this is a celebrated program. This is actually, no, these are the times when many of these words programs were used. Actually, I think I forgot this thing. So linear program, dynamic programming, etc. have this word program in them. And so some computer science people say, yeah, wow, yeah. Is there a C program or this program? It's neither. These are a bunch of mathematicians who are just basically called them programs. And in fact, there is even a story that Bellman called his stuff dynamic program because he was supposed to do serious work, which has actual impact in his lifetime while sitting in Rand Corporation so that we can win over the Soviet Union. And he was doing these theorems. So he came up with this idea called, let's call it dynamic programming. They won't know what they're doing. And so he called it dynamic programming. Okay, I don't know why the linear programming came after or before, I don't know. So that's one of the historical things. So anyway, linear programming is known to be polynomial. It's known to be polynomial. And so if you can take your problem and convert it to a linear programming problem, and if the conversion is not taking exponential time, then your problem is polynomial. Right? Remember, linear programming is an optimization. Right? Basically optimizes. So computing the optimal policy is posed directly as a linear problem. And because linear programming is polynomial, you know that actually MDP optimal policy computation is polynomial. It doesn't come from the value iteration. Even though people mostly use value iteration, which actually has expected worst case exponential time. And the strange twist in this whole thing is who told you that linear programming is polynomial. It turns out that the most well-known algorithm for linear programming is Simplex. George Danzig came up with Simplex algorithm. And essentially the idea for that is if you have essentially a two-variable situation, then all the inequalities would be basically hyperplanes. And so you have a polygon. And the feasible region is inside of the polygon. And the point that you can understand, if you understand the theory of linear programming, is the optimum of your objective function, whatever it may be, has to be in one of the corners of the polygon. Okay, and since there are only finite number of corners, hey, it's good deal. It's what I'm saying. And what Simplex does is goes from corner to corner to corner to corner, finding the best corner and stops. The sad part is if you think of the input size as the number of variables that are given, the x1 to xn, then the number of intersection points in 2 dimensions will be a polygon, n dimensions will be a polyhedron, n-dimensional polyhedron. And you still have to look for corners. The number of corners of this polyhedron would be exponential in the number of variables. Do you understand what I'm saying? Like even if you have just 2 variables, right? Then I can do like if you have just 2 variables, I can have a polygon like this. They're all piecewise. So huge number of piecewise things, there are many corners. It's not just 2 corners. That's all you need to know. So there can be exponential in the number of variables. And so actually simplex algorithm, worst case complexity is exponential. So for the longest time in computational complexity, people didn't know whether simplex is actually polynomial or not. It was one of those unsettled questions. And then basically people found interior point algorithms. Interior point algorithms start inside of the polyhedron and gradient ascent their way. Not exactly gradient ascent, empirical gradient ascent to the right corner. This space is infinitely large, right? Because the number of points inside a polygon is infinite. Number of corners is finite. Number of points inside a polyhedron is infinite. But it turns out that the interior point algorithms have worst case complexity, that is polynomial. Which is why to show something is polynomial, you just have to provide one algorithm that solves it polynomial. Right? You don't get to say, what do you mean sorting is polynomial? I just wrote an exponential algorithm for sorting. So they just slap a silly and say, okay, that's your problem, that's not mine. If there's somebody else who I will hire instead of you, who can write polynomial algorithm for sorting. Okay. So the point is that interior point algorithms actually give the complexity of MDP to be polynomial. So not MDP, linear interior point algorithms prove that the complexity of linear programming is polynomial. And that is how complexity of value iteration becomes polynomial. Having said that, the twist is, despite the fact that you can convert linear programming and the MDP optimal policy to a linear program, nobody does that. Instead, they will either directly do value iteration or actually more likely do RTDP or Markov chain Monte Carlo. Even for optimum, they just do value iteration. Because for small sizes, that actually works better. And not surprisingly, even for linear programming, for the longest time, interior point algorithms were looked down upon because in practice, they took more time than the simplex algorithm. And you guys do realize this, right? Because, a 2 power n can be lower than a polynomial function for some region of n. All we know is that eventually 2 power n overtakes any random polynomial because its rise is much higher. So as you keep going on the x-axis, eventually an exponential takes overtakes. And in particular, what happens in these kinds of polynomial algorithms is they have this huge constant, and those constants can kill any savings you get in actual practice. So very few people were using interior point algorithms. And actually, I think now they do a lot more, but even now, many people for small linear programs use simplex. There you go for how everything in the world is connected. Planning is connected to MDP is connected to linear programming is connected to simplex is connected to interior point algorithms. Okay. Now the next question is, now that we know MDPs are polynomial, PDDL planning is what? Complexity. What did I say is the complexity of PDDL planning? Piece-based complexity. So, is it polynomial or higher?
A little higher.
Way higher. So, what did we now show? Which is harder problem, planning or MDPs? So here is the thing. So then would it be reasonable to say that if you have a planning problem, you should compile it into MDP? Because then the solution will be polynomial time constraint. How many people are going to buy this argument? Do you understand what I just said? Does it even make sense that somehow MDP is looking better compared to PDL planning? Because all this time I was saying MDP can do all sorts of things that PDL can't do. Like for example, MDP by definition can actually have trajectory constraints, this and that, all sorts of interest, arbitrary reward functions, etc. And yet it's only polynomial. While planning, which is supposed to be an easier problem, is piece-based computing. And who would ever buy your planning solution if you do it much worse only for some subset of problems than the general method? I'm very depressed that people are listening to me like this. What happened? Isn't it reasonable for you to believe that I have this bridge that I could like to sell you? It's very cheap. It's called the Brooklyn Bridge, and I own it. Since you believe this stuff, you can also believe that stuff. What's wrong with what I just said? And for 71 people, your grades have been retroactively reduced. because I made a huge deal about this in that class. What happened? It looks like a paradox. It can't be a paradox. It must be a fallacy. What's the fallacy? You understand it has to be a fallacy, right? Because the easier problem can't be harder than the harder problem, right? So what is wrong? Because you guys are forgetting the fact that complexity is always in terms of the input size. Planning problems complexity is computed in terms of the number of literals, n literals defining the states. If there are n Boolean literals, the actual number of states is 2 power n. So if you compile it down to atomic MDPs, you will get a 2 power n sized MDP in which you can be polynomial. This is what I'm saying. You should never fall for this. You should make other bozos who take other AI courses fall for this. I'm so sad that you fell for this, right? You understand what I'm saying? Basically, because it's all about input size. And in fact, there are bunches of things. I mean, all of these I have tweets. For example, you can always compile a symbolic problem, by taking Bloxworth planning problem and take pictures of it. And then all of a sudden you have much bigger state space. And you can say, I'm polynomial in that state space. That's bosoness. You should really be, you should basically you just increase the state space size so much, whereas the other one is actually fixed state space. And you should be able to do much better than being polynomial in this hugely increased state space size. Yeah.
So in summary, it's a scalability problem where the more you scale up, the less and less efficient it becomes.
No, I'm sorry. This is a theoretical point I'm making, which is that worst case complexity is decided in terms of the input size.
Yeah.
Planning, PDL planning's worst case complexity is decided assuming that the input size is measured in terms of the number of variables, which is logarithmic in the number of states. So it's exponential in the log of number of states, which is polynomial. Remember, if you actually converted PDDL, I mean, again, this is the thing that you will get whether you like it or not from this class. It may not help you right away say, oh, I have this new algorithm, etc. But you kind of understand how these algorithms are connected. Okay, so planning cannot be worse than MDP. MDP is currently in the atomic space. If you consider the planning in the atomic space, it will be A star search. A star search is polynomial for the kind of state space you have. So it's actually surprising that MDP is polynomial. It should be worse. Okay. And never convert PDL planning into MDP to solve it. That's the easiest way to kind of, again, you can get points because then you get to say I'm doing RL because MDP is connected to RL. But you could also be deluding yourself because you essentially lost the entire structure. Okay. Yeah. So anyway, having said that, I said also RTDP is the only thing that people mostly use, and actually even more so than RTDP, you actually use Monte Carlo research, and you should know those things more because you no longer compute the optimal policy, you compute something closer to the optimal policy given the amount of time you have. Okay. Any other questions on this particular thing? Okay, so those are your value iteration, finite horizon value iteration equations, and the normal, and you should have seen this. This should not, if this is looking surprising to you, then you didn't see the lectures. So this was essentially finite horizon value iteration in an operation. So you start with V0. V0 will always know, you know the value, V0 is R0. And V0 will just be the reward, because if you can't do any more actions from the state, whatever reward you got in the state is your value. And then the other states, the actions that you can do, A1 and A2, A1 basically with 0.7 gets to this and 0.3 gets to this. And so 0.3 times the value of this plus 0.7 times the value of this is the expected value from the A1 side. And similarly, you can get an expected value from the A2 side. And the value in the next horizon bound for the same state is the max of these two, because you have, that's what makes you macro decision process. You are never going to take the less of the two actions. And what you just did is the graphical version of what was written here, which is the Bellman update equation for finite horizon case. Okay. And the other thing to remember, and then so if this thing looks somehow like this, then you turn it around, it basically looks like a game research. Here you're playing games against the nature, and you're just propagating the values up. And once you see those two pictures together, you know how many ideas can transfer from game research to MDP and vice versa. Okay, and something like normal value iteration goes like this. So you start with V0, which will be R, and then you will compute the V1, then you compute the V2, then you compute the V3, and then V15,000 and V15,001. If the max norm is not changed, then in the infinite value case also you can start. If it's finite, you just do the number corresponding to the price. Okay. Like I said, mostly people do RTDP, which is essentially, give the, without actually, give the values to the lowest level things as a heuristic value, either as a reward or some heuristic value you computed for them, and then you do Bellman update to back up the values. That is RTDP. And RTDP looks very much like game trees. The deeper you get to push the RTDP tree, the better the evaluation is at the node you're about to do. And these are called the online algorithms, because you are at this particular point, you're trying to figure out what's the best action to do. And you go as deep as you can in the time you have and see which of the actions are getting better backed up values. And this is expectation and maximization. Again, it's not the EM algorithm, but it's like the normal game tree is min, max, right? Here it's expect, max, expect, max. Nature does expectation, we do maximization. Okay, that's what is RTDP. And Monte Carlo research, I should say a little about it, because oftentimes it's not covered, although it was covered in my lectures. It's worth understanding because everybody uses this these days. And I kind of said this in words. I'm saying too many things in words, and I need whisper so that it can convert it into English. And I'm telling you, whisper apparently works very well. So somebody took this Telugu movie trailer and fed it to whisper, and then it gave the English subtitles. I actually tweeted it, and that's like Babelfish right now. Guys know Babelfish? So Babelfish, Babelfish is Hitchhiker's Guide to Galaxy, Golubita. So you just put this fish in your ears, then every language you can understand. So you throw in Whisper, then you guys all can see great Telugu movies. I don't know whether you can enjoy them, but you can see them. Okay, so the point is that the Monte Carlo research is used quite a bit, and the words in words I explained to you that unlike the way RTDP does, which is it goes level by level by level, essentially it goes k levels deep and computes the entire subtree and backs it up. What Monte Carlo does is instead of doing that, it basically goes through one rollout, what they call rollout. What's a rollout? You start from where you are. You pick actually these particular slides are defined in terms of the game. So this min and max, but if you can do the MCT for expect max, where the nature just picks random. Okay, so you pick an action and you basically sample one of its outcomes. You pick an next action from there and then sample one of the outcomes and so on until you reach a terminal state, or at least a state which is fairly deep. If you have MDPs with actual terminal states, then you can keep doing this until you reach a terminal state. The moment you reach a terminal state, you know that the reward at that point is the true value of that state at that point. Except it's a single thin probe. Okay, and so the point, of course, is then you can update everybody on the path to this. Their values, the estimates of their values based on this probe. That's what MCT is. The difference is, in the case of Monte Carlo research, the problem is it may well wind up picking the same action every time under a particular, a particular state, quote unquote random being not fully random, at which point it's likely to not see the rest of the state space. You understand what I'm saying? This actually leads to the same problem that you talked about in reinforcement learning, called exploration versus exploitation. Now, my first question is, why aren't we talking about exploration versus exploitation in real-time dynamic programming, RTDP, but only talk about it in MCTs? Yeah.
Because you could theoretically keep going forever in MC.
No. In RTDP, you never chose. You kept all the guys under every node. You see what I'm saying? You decided the depth you can go to, but you considered all the directions under every node up until that depth. So there's no bias in I'll always be going left. Do you guys understand that? Whereas MCTS has to pick one outcome at every point so that it can have a deep probe. The point is, if it doesn't truly randomize, then it actually can basically be, have the same problem that RL has, which is you will be optimal with respect to the incomplete world model. In this case, the world model is the search tree configuration, not the real world at all. So one idea could be that you can just make sure that you are random, that every place you actually toss a coin and pick, one of the outcomes. But then you should do the other thing where you always go left is efficient. It will kind of converge to a good outcome faster, but it's just a very biased outcome. The one that's picking uniformly random is going to be inefficient. It will converge to the true optimum, but it's likely to take much longer. And the reason, the difference is that what you want to do is you want to try the alternatives that haven't been tried as much before. You understand? What is exploration? Exploration is not doing the same thing many, many times, as doing everything exactly once. It is essentially with a higher probability do things that, if everything else being equal, try to do things that haven't been tried before. But at the same time, you should try things that are like definitely likely to be bad. And so there is this beautiful idea that you should read up called upper confidence bounds algorithm, which essentially gives you a weight for each state based on its current valuation and based on how often this node has been visited. And it's inversely proportional to how often. And so there are two parts to the value. One is the valuation, current valuation. The other is a little bit of bonus. And that bonus depends on inversely on how often this node has been visited. If it's been visited lots of times, then whatever value you have is probably your value. I'm not going to try it again. But if you have been visited very few times, I'll give you a little bigger bonus, just so that you look as if you have a higher value. And then I try to do greedy selection with respect to this increased value. If you look at this, this is pretty much what RL does in exploration exploitation trade-off. In fact, if you heard the RL lectures or have done RL before, the way you increase exploration is you try to increase the current estimated value artificially, such that the things that haven't been tried as much are given a chance to show off their colors. And if you don't do that, then you will never be optimal. In fact, I argue, I think this part is from last time, I argue that this is actually the best argument for affirmative action. You should try having everybody do everything because you don't know what you're missing. If you make them try, and if they actually are bad, then at least you learn something. Assuming that since bald white men or bald bound men are the lecturers that I've seen, we'll only have them as lecturers, is essentially going to get you stuck with me. Okay, you should try other things, and then the society will basically reach a better optimum by ensuring that you have given a chance of trying nodes that haven't been tried. That's what upper confidence algorithm is doing. That's what exploitation does. So you see this beautiful connection between Monte Carlo tree search, which is a search that is being applied to Markov decision processes, which has a fully specified reward and the transition function. So there's no learning. You understand what I'm saying? It's a pure inference problem. The learning is happening in the search. Whereas the same idea, when RL was using it, the learning was actually happening in the state space itself. It didn't even know this other state existed, because one day there was this one funny door that you had in your home. You never opened it. It was always closed. Why should I open it? And one day you opened it, and then it was like a very stinky place, so you learned something. And one day you opened it, and there was like gobbles and gobbles of spoiled cake. You learned something. Gobbles and gobbles of gold. You learned something. You learned that there is actually a state. In fact, there are all sorts of crazy videos that people have shown where this woman was in an apartment in New York or some city and found that behind one particular false wall, essentially there was an abandoned mall. I'm not making this up. There was an entire abandoned mall. And this basically, this mall was abandoned, and they just made this little part into an apartment, and this woman rented it. And she always felt there was something else. I guess she opened it. Right? I mean, the kind of thing that we do when we see horror movies, saying, don't do it, don't do it. Right? Is actually you should do it. It's for the good of the humankind. You might die, but hey, exploration is very important, and it's actually on that note, we'll take a 15-minute break. When you explore, you can die, which is why you don't explore most of the time. But we learn. Human society has progressed because bozos explored. But if you are exploring in search, you don't die. Monte Carlo tree search never dies. It's just exploring in search. RL with simulator, which does exploration, never dies. Real RL would die. That means if you're actually trying, oh, looks like this part of the Grand Canyon looks like a very nice shiny pebble. Let me stand on this. Rest of the class is out. Instead, what we will say is for bozos like me, they would have generated like a Grand Canyon simulator, like a flight simulator. So that I can mentally see, okay, what if I stand like this? Doom, you die. Oh, okay, I die. Okay, I won't die now. I'll just not do this action. But in real life, you die, you don't get to. I mean, unless you really believe in fast incarnation. Sure. So other people do learn. That's actually the beauty of human civilization. We learned because of bozos doing reinforcement learning. Those people are no longer there. But we are here. We were just sticking to tried and tested routes. Don't touch this thing. Don't try to pet a tiger. Don't eat this leaf. Oh, you want to try eat. And if you start looking like a Superman, okay, maybe guys, let's all eat that. And we just, that's how we survived. We needed these people who explore, not ourselves. We should just stick to tried and tested things. Still go to Brown, Balding professors' classes, but they should be classes, but anyway, 15 minutes.
So you have like a bunch of like ratings and qualities as we feel like sort of systems sort of like so in this case from like a line and then a quality.
Now we have reached.
That's the signal. That's the signal.
That's why I think it could be an interesting TD project because not the great solution won't always work. Like if I go for Weaver, I go for National Explorer, you'll track yourself from the areas.
I was talking.
This is the solution that we get in. And
Sign up sheet to the.
there is just such a swath of things that interact.
No, you're doing it. That's fine. That's
I wasn't that sure about that.
okay.
But
I believe we
I
are
mean, it is a big enough state system. Like,
the time. So there is an attendance sheet going around. Make sure that you kind of sign up. That's why I know who's here. So continuing along for the couple of things that are worth remembering. Again, there's just so many variations in the way RL frameworks are given that it's worth remembering that transition can be written either in terms of R of S, or it can be associated with the actual transition R, S, A, S dash. And so for each transition, you get a different number. That still is Markov. Even though it depended on you started from S and going to A and S dash, that's still close enough to Markov that you don't have to change the state space. Most of the algorithms still work. And then in basically, if you either give RS or RSA S dash, then you try to maximize the value. That's the normal RL thing. That is like the, they are optimists. They think that is value to be found in the world and you have to maximize it. And then the control theorists basically look at MDPs in the cost terms. And so there is a cost associated with either each state or cost associated with each state transition, which is closer actually to the planning world, actually, because planning world, you assume actions have costs and goals have utilities. Okay. And then the goal is to come up with a policy that minimizes the expected cumulative cost. So this is you're maximizing V star, you're minimizing J star, and essentially the same ideas with just the duals, not even duals. It's just one is minimization version problem, other the maximization problem, but all the theorems looks the same. So if you take typically like Dimitri Vatseka's course on reinforcement learning that he teaches in spring, he will mostly think in terms of cost because he comes from control theory. Okay, so it's typical view taken in search and control theory, typical view taken in RL community. And then you also kind of, oh, this is kind of unfortunate that kind of missing all this stuff in this thing, but the dynamic programming equation itself winds up changing. This one actually, let me see if it is. Yeah, the dynamic programming version itself winds up changing, depending on whether you're using RS formulation or SAS- formulation. Okay, and so that you want to keep in mind. In particular, when you have the SAS- formulation, then you essentially maximize. You put the SAS- inside the maximization part, because the other one, as soon as you get to the state S, you already have RFS. So you put that and then add to what changes you do. It's what you should remember these variations. Okay. So here basically this will be R of S plus beta of max, blah, 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 and for all S dash, this TSAS dash V star S dash is basically being updated to V star S. So that's the normal, simple RFS formulation of reinforcement learning. Okay, so we're talking about now, actually there's really very, very, very little difference between RL and MDP and search in general. In the real difference is, in one case, you have the model in hand, the other case, you learn, and the world model is in hand, in the case of inference, and the other case, the world model you have to learn by acting. So the pure RL involves actually acting, but many RLs that you actually look at wind up having a simulator, so they're actually calling the simulator to tell them what happens if they do this state, if they do this action in this state. So in that particular case, reinforcement learning is very much, as I said, similar to the planning reinforcement learning difference is similar to CSP-SAT difference, because you just have a black box simulator. You say, I'm doing this action in this state, tell me what states will come, and it just sample, it will tell you what state comes. Okay. So I'm assuming again that you have looked at RL parts, and you should. The one interesting difference is that in the case of RL, you're assuming that the agent directly doesn't have a model, and it still is trying to compute the optimal policy. So it could first compute the model and then compute the policy with respect to it. So then you can subhold to the MDP. So first try to learn the model, and typically you try to learn the transition model, and that you can do by just acting in the world, keeping track of how often when you do this state, how often you went to these other states, take some frequencies and use that to convert the probabilities. Essentially, that way you'll have computed the model. And of course, that model is as good as how much have you acted in the world. If you haven't seen certain parts of the world at all, like, you have this hidden bureau that you never opened the door of, you didn't know what happens, what's there behind it. And there may be like large amounts of very high valued states there, and there are interesting actions you can do there. And if you didn't do them, then you don't know that state, part of the state space. Okay, so the big difference between RL and MDP is MDP assumes that the state space is in front of it, at least in an intentional form. RL assumes that you have to learn, you have to basically experience. Okay, now given that, one interesting question, of course, is since the main thing that RL needs to do is compute the optimal policy, it can just directly compute the policy, or it can compute the middle part, as I said, model, and then convert it to the policy. And if you do the first one, then, so if you do the learning transition model first and then convert it into the policy, then that's you're doing it MDP as a subroutine. Okay. You can also just essentially directly learn the MDP value. At the moment you compute the value, then you know the policy. Okay, there's a small difference. Actually, one thing that you would realize, you must have realized by now, is the value function V of S is typically not good enough. Instead, it's better to learn the Q values, Q of S of A. That is, what is the action? What's the expected value of doing action A in state S? Okay, and then value function V of S is nothing but max of Q of S of A. You see what I'm saying? And if you learn the Q values, then you can convert it into actions for the policy, even if you did not have the model. If you didn't learn the Q values and you only learned the value, this you should understand. If I just gave you the value and you don't know the model, you can't, you know that, okay, that neighbor, they are having a lot of fun. I know that they are having fun, but I don't know what action will take me there because I don't have an action model. Do you understand what I'm saying? Okay, so that's something that you have to do. So VFS is what we typically talked about up until you came to this quote unquote model-free reinforcement learning, where you don't want to learn the model. But if you don't want to learn the model, then I made this argument point last time that if you know the V star, you can get the Y star. That is assuming you have an action model. Do you understand what I'm saying? V star can go to Y star if you have the action model, which is TR SAS dash. If you don't, then essentially you say, I know you guys are having fun, but I don't know how to join you. I don't have an action. I don't know what my actions do. I mean, I have to, you can of course always say, try, you know, whichever, but you don't know obviously which action will get you there because you didn't actually keep that information. If on the other hand, instead of computing values, if you compute the Q values, which would be, you know, if there are like 10 actions per state, then the number of Q values will be 10 times the number of values. But the moment you do this, then at every state, you just keep that Q value that's the highest, if you're in the maximization case. Okay, that's why people tend to talk, the more you hear about Q learning, the more you know that they must have been doing model-free learning. Because you don't need to talk about, I mean, there's nothing wrong in talking about Q, but you know, if you are anyway finding the model, then you don't need to keep the Q values along, you can just keep the value along. Okay. So that's the distinction that I assume you guys got. And then so in essence, from experience, you can get the model and then do planning to get the value. From experience, you can go directly to the value policy. And this shortcut is called model free. This longer version is called model based. Okay, right? That's the difference between model free and model based. And then there are typically two kinds of reinforcement learning algorithms, two families that you have heard of, you must have seen, which is passive versus active. Passive or else basically they are just trying to figure out the values of the states while they're being transferred from one state to another state. So that means the policy has been fixed. You see what I'm saying? So my example, if you heard my lectures, my example would be, you're a kid, your mom basically ties you up in the back of the car and you don't get to say, hey, mom, I'm going to go to the ice cream store today. No, you have no choice. So you've been tied and you know, she will be doing her chores based on her own policy. And yet you might start finding, you know, a kid or a dog, there's not much of a difference. And so then you realize that whenever you makes this turn, typically that leads to eventually some amount of sweetness in your mouth because that's where the ice cream store is. So as soon as you make this turn, you know, you start a hand and your dog will start, you know, basically wiggling its tail. So it computed the value of the fixed policy by experience. Okay, so that's basically passive reinforcement learning. Active one essentially, so it's just there, the value, the policy has been decided by somebody else. You don't get to change it. All you can do is which states are good. Yes.
We're calling passive and active.
What?
Are these sometimes called like on policy versus off policy? Or am I just?
There is a connection there. I mean, in general, so the on policy, so the passive and active, they're very good connections. So let me point that out. So if in fact you don't have any access to your own policy, then you are always doing just passive reinforcement learning. If you do have a choice, then you can either do, then the possibility, if you get to choose, which is the active reinforcement learning, in the case of active reinforcement learning, you can either take the current policy and use it mostly to do actions with some epsilon disturbance, which would be kind of on policy. Or whatever policy is there, ignore the policy and just try to do actions, because you can do actions. The bigger issue is you can do actions. So notice the same kid analogy. After a while, the kid becomes a little bigger and actually knows, they're able to actually walk around and they can understand mom's instructions. Mom says, I'm going out, don't do anything bad. And so basically your policy has been decided by your mother. Say, you can go up to the, this chair and you can sit down, you can go up to this one and do this. That's the policy that's been given to you. But you do have the choice. Now you can actually do actions. You are not tied up. So you may decide to essentially explore anyway, even though that's the policy that should be followed. And this is the kind of distinction between on versus off policy. Okay, to even actually talk about on versus off policy, you need to talk about the ability to do action. In my case, the kid was actually tied up in the back of the car. The kid couldn't do any motion actions. That's like a pure on policy. That's the pure passive. That's like the word passive. Okay, when you can be active, you can choose to be passive. That is the on versus off policy difference. Okay, in fact, there's like a ton of different small variations in the RL algorithms. Okay, but there are also a ton of different small variations in the planning algorithms. Maybe it's a smaller world, but there's still lots of differences. And you want to kind of understand the major dimensions. Okay, and then that's the model passive versus active, and the model based versus model free. I essentially explained to you. And one crucial difference as to why should anybody care about having a model is the model allows you to simulate. If you have learned the model of the world, then you can simulate with respect to that model. You don't actually have to execute. So you have to ask yourself the following evolutionary question. Okay, originally we did not probably have, right now kids are born with evolutionarily equipped models of the world. You do realize that, right? Kids basically, the brains are already structured in such a way that, for example, kids' brains are primed to learn any human language. So if, for example, you are a Tempe resident and then suddenly after the kid is born, you decide to hang around in Betapuram, I'm telling you, your kid will speak very good Telugu. There's no worry. If on the other hand, you're a Tempe resident and you got stuck in the wolf land, your kid will never speak wolf. There's such a thing as wolf. Okay. So basically, all human languages are in one particular, some high dimensional manifold of languages, and our brain is equipped to learn any of the human languages. And it's gotta be, right? Actually, it's very interesting that is the case, because in the old days, our ancestors weren't really taking flights and going after various places, but evolutionarily, that was what we had. So we have actually, the brain has a significant amount of model already, but at the beginnings of the evolution, if you situate yourself the exact time where you may have separated from primates, even though primates also have models that we have inherited of the world. Like object permanence is something that most animals have, for example, that we have inherited. But imagine that there was a time during the evolution where certain parts of your world, you don't have any models at all, right? And so you do, through experience, you are computing the models. And because now you have models, you can think in your world, if I were to do this, what will happen, without actually having to do it in the world. If you don't have the model, the only way you can figure out what happens if you do an action is actually doing it in the world. Doing it in the world is inefficient because actions take tons and tons of time and dangerous. Right? Whereas thinking about doing is what we are all very good at. Yeah, I'm thinking that I'll be doing this project for this person. It's real. Makes you feel good, right? And you are simulating what would happen if I were to complete. And so that requires some kind of a mental model. some kind of a model of the world. And so the model based versus model free, the big difference is whether you can simulate the world or not in your head or not. Ultimately, okay. And there are certain things where, and ultimately, since it looks as if, based on this, looks as if every problem can be done either model based way or model free way. That is true. But it turns out in real world, certain problems we have models, certain problems we don't have models. You know, a classic example of a activity for which we don't have model is swimming or even walking. It's not like you can visualize how am I going to walk from here to there. The moment you do that, you'll actually probably get leg tied and fall down. The same thing with swimming. Essentially the way to visualize swimming is to swim. Why is that? You could have learned a model for swimming. It's a very interesting point that given the mental limitations we have, the model for swimming would likely have been so large, so non-compact, that there was this trade-off of learning this huge, large model versus just do it like Nike way. Right? The interesting thing is swimming may well become, it may well be the case that if we don't have the mental limitations we have, model-based swimming may actually be good. Did you understand what I'm saying? Right? I mean, if you have if you are going to put a 300 billion parameter world model for swimming, that you're just going to only learn swimming on that, okay? There you have the model. The reason we don't do it is because that would basically use up most of our brain, probably. Or we feel like it's not worth it and somehow we don't simply do it. So the tacit versus explicit knowledge distinction is kind of connected to model free and model based. Okay, and in some sense, what is tacit for us may well be connected to our mental, the mind, the brain limitations, and it may well change. In theory, actually, anything can be done model based or model free. Do people understand what I just said? Okay, swimming is a classic case of nobody seems to do it model based. Travel planning is a classic case of nobody seems to do it model free. I just go stand in front of that, like whatever the airline counter and say, hey, tell me what the flight is. You never seem to do it. It's like a dumb idea. Right? But the point is, you could do it. You could do model free travel, you could do model based swimming. And that's kind of, I should say, you could do model based swimming and model free travel planning. Even though currently we don't. It's worth understanding that. You see what I'm saying? And essentially, as much as people keep saying that machine AI, the goal of AI is to reach human level AI, that's all bogus, basically. Because essentially AI has always been better at being superhuman in narrow slices than being like human across the floor. It is what I'm saying. LLMs is certainly not the way we learn language. But it seems to work in some sense in terms of completing sentences. Okay, so they have very different kinds of limitations. And so it may very well be that what we understand as the model-based versus model-free canonical tasks might change. Ultimately, it's really a question of is it worth, how big is the model? And if there's a compact model to be learned, then it's worth learning it because then it can allow you to do simulation. But then nothing is ever isolated in this world. Whether or not your model can be compact depends on whether or not you have good abstractions for the task. If there are very good abstractions for the task, there may well be a compact model in that abstract space. So for example, Block's world planning is model-based, but it's model-based in the context of PDDL operator, PDDL symbolic representation. If you're trying to do Block's world planning using deep reinforcement learning from pictures, and close enough to that is the Atari game suite that the original DRL was being used. They never did model-based, they did model-free. Why? Because essentially they were not doing much of an abstraction. They're essentially trying to learn from the pixel space. And if you don't get enough of an abstraction, there may not be any major advantage. Of course, there's a disadvantage of not having the model because every time, so this is one of the reasons that model-free people tend to think this, I mean, we'll talk a little more about it. This whole issue of generalization becomes, I already said this once in the class, becomes like a big thing. Okay, as I said, you change one pixel in the picture of the initial state, and you can still solve the Block's world problem. You generalized. Originally, you were only supposed to work for picture 1 to picture 2. Now you're working from picture 1 dash, where one pixel value has been changed by a little bit. So it's a different picture. To picture dash, to picture 2. You generalized. It's, when you talk about generalization, the question is what sort of meaningful generalization is it? If you generalized your Block's world knowledge to be able to start doing ship, putting boxes on the ship, that's a nice generalization. On the other hand, you generalize Block's world planning with red blocks to Block's world planning with green blocks. That's generalization too, because you only did red blocks and now you're able to do the green blocks. How can you tell you did not generalize? You did generalize. It's just a very low level. They haven't done any abstractions. Okay, I bring this up because generalization is this overused word in RL. And you need to think of, would you have called what they're doing generalization if it was kind of symbolic? If not, then at least it's a different level, much lower level generalization. Okay. Yeah. Okay, and then as I said, you could do simulator instead of the world, and then if you're using the simulator, then you're using somebody else's knowledge because somebody built that simulator. Unless the simulator itself is the world, we are living in matrix, and simulator itself is a world, right? Basically, if somebody gave you the simulator instead of a world, then they figured out how the world works. How the heck did they write the simulator otherwise? You know what is the best simulator of the world? The world. Right? I mean, in fact, in India, we used to have this thing that the weathermen and weatherwomen will say, the weather is, and they'll come out of the studio and say, raining, and they go back. It's model-free weather prediction. Because you just use the word as its own simulator. Okay, it's very inefficient. I mean, weathermen typically don't die. I mean, unless they also get struck by lightning when they went to see it. But in general, it's a very inefficient way to actually simulate the world in your mind. Okay, so that's important. Okay, this is basically the same RL review. I mean, just said the same thing. I mean, that I said those two slides are saying the same thing here, except I just want to rewriting it again. But the one important thing in the active RL is you need to, as I said, I'm repeating myself, you need to actually not just do what's working. You try doing things that you haven't done before. You understand what I'm saying? I mean, did I mention the kids who are like world-class crawlers? Like when you're a kid, motion is very important. You're intrinsically motivated to move, right? Because good things seem to be happening, not so bad things, but mostly parents would have removed all the bad things from happening. If you move, you seem to have good things happen, Either somebody might kiss you, or you may, fall into a bag of cookies, and there's sweetness, all these internal reward metrics. So you need to move. All you need to do is move. Okay. So you learn crawling first, because that's the fastest one. It's actually very interesting. Why do kids learn crawling? Because that actually turns out that we were all supposed to be quadrupeds. You understand? In fact, somebody just said yesterday that it's a dumb idea that we have humanoid robots, given that evolutionarily quadrupeds are the most stable things. I mean, there's a thing called cow tipping. There's no thing called people tipping. People can be tipped basically by just kind of, under the star itself, they're getting tipped, right? So the quadrupeds are actually the best, most stable things, right? And so the interesting thing is that, you start crawling on all fours, right? The interesting thing is that some kids become extremely good at crawling, and then they're not walking, and their parents are taking them to specialists, saying there seems to be something wrong in the walking part of his brain or her brain. Can you kind of switch stuff? But what the kid is basically doing is the kid doesn't have too much of an exploration with it. The kid is doing, I'm getting all the cookies I need by crawling. Is there anything else left in the world? What exactly do I need to do to stand up? Why do I need to stand up? And then if by somehow people make them stand up or something, then they might start seeing some other things and they'll start learning this thing. But that standing up is exploration, because something is working. Why do you do something else? You see what I'm saying? So active reinforcement learning involves exploration versus exploitation. Right? So given, if this kid, essentially, imagine the following thing. On a particular day, this kid is still between walking and most, champion crawler, they still haven't figured out walking. They see a nice big cookie right there. They're thinking, should I kind of impress my parents by trying to walk to this cookie? Or just the heck with the parents, crawl to the cookie and eat it. What would you do? Be greedy. The greedy policy is crawl the heck out before other kids take that cookie. But if you keep on doing the greedy policy, then you are never doing the walking, you're never learning walking. And so you have to put some exploration for that. So the exploration exploitation trade-off becomes very important in general in RL, because you don't have the full model. Now, the very interesting point that I want you to understand is exploration exploitation works both in real world and in simulator. Right? That's what happened when you're doing MCTS. We talked about exploration exploitation. MCTS is doing basically simulation. It doesn't really have to do anything in the physical world. And yet, by not asking your simulator what would happen if I were to do this action, you will not know what will happen if you do that action. And you might say, why should I waste my time asking my simulator? I already have a pretty good action that seems to work. Okay, it's really a question of having the model in front of you versus not having the full model. And again, RTDP style things don't need to do quote unquote exploration, because they're asking all possible things that you can do at every level. RL by definition is more like MCTS, except in the real world. Because you are actually having an experience, one experience. You're not basically, unless you're simulating in your head, if you're actually having an experience, the experience is actually a rollout. You understand what I'm saying? And so that experience can be done in the real world, or it can be done with respect to the simulator. If you do it with respect to the simulator, it becomes MCTS. If you do it in the real world, it's just RL. That's why MCTS is like RL. You understand what I'm saying? Okay. So that's active versus passive model-based learning, blah, blah, blah. And then again, as I said, there are multiple ways of doing exploration policies. One of which is you basically do the greedy thing, P with some probability P, you do the greedy action, and with probability 1 minus P, you do one of the random actions. And as to what is the greedy action depends on whether you're doing model-based or model-free RL. If you're doing model-based RL, anytime you're about to pick the action, you very quickly convert the model into the optimal position with respect to the model that you currently have. So it's only optimal with respect to that limited model. You see what I'm saying? And then just do that action. And if the probability with probability 1 minus P, you just do one of the rest of all the action, any action randomly. And you can do better by saying, I do actions that I haven't done. If you kept track of the kinds of actions that I have done from this state, I put some more memory, then I can avoid being just random and say, let me try something new. In fact, one of the very interesting questions is, why do we crave novelty? It's also well known that, humans, like younger humans, crave novelty more than older humans. So people like us basically crave novelty, right? So the question, of course, is, why do we crave novelty? Because that's one way of intrinsically forcing the organism to explore. And I'll say, I haven't done this, let me try this. As again, it's just randomly pick one. And that will become more like UCB, upper confidence. Okay. Yeah, so those are all the algorithms. I mean, you must have seen all of this. And then so the model-free learning. The interesting thing about model-free, again, actually, it's easiest to understand model-free learning in terms of MCTS, because chronologically today we first said MCTS and then we said model-free. And so model-free learning basically has a particular experience, and rather than do RTDP style tree, it actually does one specific rollout because you have one experience. And with respect to that experience, you update your back up your value estimates. Monte Carlo tree search backup is what TD update is. It's a TD update is a kind of Monte Carlo tree search backup. What is TD update? Is temporal difference learning. All that basically is saying is that if your neighbors are rich, you're kind of rich. Where the neighbors are not just by sight, neighbors in terms of action space. You understand? If I'm Bill Gates' neighbor, and I can't actually enter Bill Gates' house, he's not my neighbor in this terminology. If I actually can do actions to enter Bill Gates' home, hey, then I'm as rich as him. He has this apparently huge, big theater. I can once in a while go and watch movies. So I'm also just kind of, my value is dependent on my neighbor's values. So in TD, what you do is you kind of update, you basically initialize every state's value to some random valuation, like RFS, like what MCTS does, right? And then you basically have an experience that's like a Markov MCTS probe. And then everybody updates their estimate of the value based on the value of the neighbor they found. You understand what I'm saying? Except that they would try to do it slowly, because it's possible that this neighbor would only occur with extremely low probability. Because an action, for example, you took an action, it has 18 possibilities. One of them is really minuscule probability. And in your experience, that happened. So you are likely to kind of change your value for the previous state where you did this action. Except unless you know that that will keep on happening, it may very well be the case that you should not be changing your thing too much. Which is why in TD, you change little bit towards your neighbor's value. Your estimate is changed a little bit towards your neighbor's value. Okay, and underlying this is the Bellman update. Bellman update is being used in doing this backup. And Bellman update was also being used in MCTs to do the backup. Because the expectation maximization is Bellman update. Bellman update looks nice and funny, nice and interesting in the equations, but here it's expectation maximization. Okay. Okay, so the learning inference distinction gets murky. So again, then deep RL is nothing but RL where Q and V functions are represented by neural nets. So normally RL folks differentiate between tabular RL, which is their term for atomic state space, versus basically learning representations like I don't know what their name is, but essentially learning your own learning feature-based state representations. And that part, either you can provide some bias saying, your state is dependent on the following features, find the weights to add them up, or you can say the state is just a bunch of pixels, you figure out what the important stuff is. And I'll give you a huge number of examples, which is what deep reinforcement is. Okay. But the idea is the same. It's like much lower level of abstraction. You're looking at the pixel space. So sample complexity sucks. But people say, look, I'm able to just see and do. This machine was not able to do it before. It required at least some symbolic model. Now it's just able to do it from the pixel level. So the real question is, if you have a domain for which you actually have a symbolic model, would you rather make the machine learn it the hard way or give the symbolic model? And that was something that I keep talking about in this course. There are some good reasons as to why you might want to give the symbolic model or let the interaction be in the symbolic model, because A, it can make the efficiency better, and B, it actually also it biases the agent towards norms and behaviors that you care about. Because the symbolic vocabulary is your vocabulary. Things that can be said in that vocabulary are probably likely to be more closer to your preferences. It's a kind of a big inductive bias. Okay, the only other thing is that reward model is never learned. As I mentioned previously, reward model in RL basically assume there's no such thing as random reward model, model-based and model-free, both. In the model-based, you're learning the transition model. In the model-free, you're just directly going to the policy, optimal policy. The final goal is always optimal policy. The reason you don't make a big difference, big deal about reward model is because the moment you go to the state, if you visited the state, you know the reward. Because the simplest reward model is every time you visit the state, the reward just washes over. So there is no such thing as learning the reward. If you are the agent doing the experience, if you are watching your friends, they're having candy as well as beer, they seem to be very happy. Trying to first of all figure out what is making them happy and trying to figure out what might be their reward metric so that I too can be like them, quote unquote. That's much harder because you're actually learning from other people's experience as to what might be their reward metric. That's very hard. And that goes under the name of essentially inverse reinforcement. And that goes under the name of goal recognition. That goes under the name of essentially the general mental model. You're trying to figure out why people are doing what they do. You understand what I'm saying? And I say this, I said it to the 471 guys, I'll say it to the class here too, that when I meet people, the thing that is most enigmatic to me, the thing that I want to know most about those people is not their capabilities, which is the transition model, but their reward metric. What makes you happy? Because we more or less have pretty much the same capabilities. I mean, we keep idealizing people who know how to do nice basketball dunks, etc. But how often do you need to do that? in real life. Mostly the thing that differentiates people from people is their reward matrix. We can all basically walk more or less the same way. We can all do the same furling, blah, blah, blah. It's not the capability model, it's the reward model that actually distinguishes one from the other in terms of the behaviors that we show. So to me, I want to know what's your reward matrix, because I can then learn more about what you would do. So what would Jesus do requires what would Jesus' reward model be, not what would Jesus' transition model be. Remember, I mean, the Jesus is actually going to fly and levitate, all that stuff. You're anyway screwed. You can't actually figure out how to do what Jesus is doing. You're more or less assuming Jesus is kind of like a human. What would Jesus do in this case? You're understanding the reward. That's inverse reinforcement. Okay, that's mental model. That is plan recognition. That is goal. All of these are the same names, so they're all connected. Which is like IRL, goal recognition, mental model. They're all connected. So if you have one paper which is talking about one of these ideas, it might actually be saying something useful about other things. They may not be thinking, but they might actually be useful. Okay. Anyway, so the Q learning basically is one of the algorithms that actually lots of people use, and all you're doing is you're updating the Q values with respect to the transition from state S with action A. And what you do is you currently have the Q value of if you're in the state S, you know the Q value for A, because for each state, you have initialized the Q values for all the actions for each state. And you did an experience. In that experience, after this state, you get to this other state. Do you understand what I'm saying? So that other state has a value, which is the max of its Q values. You understand what I'm saying? So then you can say that my value really should be following the Bellman equation using this. But my value is what I currently have initialized. So I push my initialized value towards this side. That's what Q learning does. And you don't completely become the new one. As I said, the outcome might be very rare, and so you don't want to change the values too drastically. So you use a learning rate and alpha, and that alpha rate, you basically push your current Q estimate to be more consistent. That's what Q learning is doing. Now, what does deep Q learning do? It does the same thing, except instead of in the case of factor deep RL, you change the weights. The Q of SA right now is tabular for you. There's a table. But if it's a deep Q learning, then there's a network which basically spits out the value for Q of SA. And it's spitting out a bad value because initially is wrong. So it needs to be made to spit out the better value. So you want to push it towards the newer value a bit. So you have to change the weights rather than just change the table contents. So that when you change the weights, then the table content essentially will correctly change. Now, typically when you do this, some kind of generalization occurs automatically, because when you're changing the cells of a table, other cells of the table are not changed. But if all those cells of the table are being filled in by a particular function, in this case a network, and you modified the weights of this function or quotients of this function such that it will be closer to what you want in this cell, then it's also changing its valuation everywhere else. That can be called a bug or a feature, right? We'll say it's a feature, be generalized. It's like, that's not what we really wanted to do. We just wanted to change the value estimate for this cell. But since you only have this one function that kind of works for the values for everybody, the only way you can make this function have this value closer to the estimate here is to change the coefficients of the function. When you do this, it changes everywhere else too. That's not what you meant to do. But you take the credit and say, I generalized. In fact, in the intro to AI, first time I mentioned generalization is that part. If you guys remember, we never talked about example-based generalization. We went from star search to MDPs to RL to feature-based RL. Where you are essentially doing quote unquote function-based approximation. In fact, they call it function-based approximation. And when you do function-based approximation, you are getting this kind of a generalization, whether you like it or not. Just because it's generalization doesn't mean it's good generalization. You guys understand what I just said? So that's what the difference between RL and DRL is. And so if you're doing this, then you will get DQM, which is the one that, which became quite popular in the Atari game situation. Okay. Yeah, I already talked about exploration. This stuff, again, you should take this course just to understand my tweets, and some of these tweets that I said last time also can be understood now. In fact, I already tweeted about this ILP, the LP and value iteration stuff that should be known, but most people don't know. But anyway, you know that reward is nothing but H cost, value is nothing but H cost to go, V star and J star is nothing but H star, optimal policy is like optimal path, value of a policy is like cost to go of a path, optimal policy from optimal value change is getting optimal path from optimal cost to go. Remember, if I give you H star, you can convert, you can get the path. Right? If I give you H star for an entire graph, then from any node, you know the best path to the goal in polynomial time. Actually, almost constant. Right? No, it's actually OD time because it's like depth of the. Okay. And then finite horizon MDP is nothing but depth limited A star search. And greedy one step look ahead policy of V star. Greedy one step look at policy of V star is optimal is the reason. So one of the interesting things is, as I said, this is basically once you compute V star, and that means you kind of do value iteration and the value is not changing between two iterations. You say this is V star. Right? Then you can convert the V star to pi star. You can convert V star into a policy. And that would also be pi star. That would also be the optimal policy. And it's the same reason why H star will give you optimal path. Okay? And finally, it should also be not surprising that there is a unique optimal value function for any MDP, but not a unique optimal policy. Not a big deal, because real numbers are basically value function is the same for everybody, the cost to go. And there may be more than one action that you can do, which are equal cost. And so you may well wind up picking, one of them randomly. So you'll wind up having a different optimal policy. You understand? Okay. One last thing is that, so V star is unique. Pi star is not. There can be more than one optimal policy. The other question is, since pi and V are so well connected, at any given point of time, if I have a V, I can convert into a pi. I don't have to wait until the V star to convert into a pi. So one idea, which is what policy iteration does, is basically think of doing value iteration. After every iteration, convert the value into a policy, acting as if that value is the optimal value. That would be what's called the greedy policy for that value. Do you understand what I just said? So I give you an H value for your graph. And I say, I don't know whether it's H star or not. Maybe it's H star. What would you do if you believe this is the right one? Then you would say, using that, I will pick the neighbor that will have the shortest path according to this. That would be my greedy path. Similarly, I can have a greedy policy. Every state will pick the action that will have the best expected value return according to this value V rather than V star. One step greedy look ahead. Now you have a policy. Now you convert the policy into value. It turns out that given a policy, we didn't talk about it in this class, but if you saw the lectures or if you read 471, you know that given a policy, you can compute the value. And in fact, it's a polynomial time operation. There is no maxes. It's actually given a policy, then you get a series of simultaneous equations connecting values of various states to their neighbors' values. Simultaneous linear equations. And simultaneous linear equations are extremely cheap to solve. So you can convert value into policy. So you can convert, you went from value to greedy policy and from greedy policy to a value. Now this value would be different from the original value. Now from this value, I get the greedy policy from here. So I'm sort of bootstrapping myself and levitating. But it actually works. Why? Because a single policy corresponds to a unique value function. But a single value function can correspond to multiple policies. And so if you're doing policy iteration, interestingly, between two iterations, I can just check if anywhere the action has changed. If it didn't change, then the policy hasn't changed, so I can stop. Unlike value iteration, where you see if the value has changed by epsilon, here I actually check if any action discretely changed. So policy iteration is actually going to be circling through a finite number of policies. Value iteration is going to be circling through an infinite number of value functions. In fact, policy iteration has the worst case complexity that is better than value iteration. Just like the plan space planning, forward and progression and regression, this is also one of these undying battles. Policy iteration should be better than value iteration, but it doesn't actually do well in practice. You understand what I'm saying? And in fact, if you think in terms of, and also you can talk about why does the policy iteration actually converge? And it converges for the same reason value iteration converges. Because I'm giving you value, policy, value, policy, value, policy sequence. Ignore all the policies. Then it's value, 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 value sequence. Between two values, you got the second value from the first value by some number of Bellman updates. Bellman update is contraction. So if the value function, value iteration converges, so does policy iteration. It may actually converge faster. It actually converges faster. But it takes more time because the per step evaluation is faster. Okay, so that's that. And okay, one other thing I want to mention this one is that reward metrics, I actually said this quite a bit in the beginning itself, but reward metrics that has been used by RL should be seen as a much more generalized notion of goals than what A-star search uses, which says a certain sets of states are the goal states. Reward metrics basically can also capture trajectory goals. But in general, as I said in the beginning of the class, reward metrics which are trying to capture trajectory preferences, such as walk more gracefully, would be non-Markovian. And so typically that would mean that you have to expand the state space, if it's finite state space to begin with, to make it Markovian again. And so whenever people talk about trajectory goals, then you know that they typically are probably expanded the state space. But as I already said in the beginning of the class, if you already had infinite state space, then you probably could care less. But if it's a finite state space, you can actually tell how much it's worth. Okay. So essentially, this is where I would probably will stop. But there's a piece that I'll ask you, make you look at, which is actually a summary of the last two classes from the perspective of people who know planning and people who know RL, which is what I more or less expected you to be, but I kept giving you background information. And so I gave this talk in the planning, bridging planning on RL in summer. And the first part of that is planning versus RL. And in fact, it essentially makes most of the points I have made, except in much fewer slides. Okay. One thing I do want you to understand is in that part, I talk about model-based, model-free stuff that we already talked about. But the other thing I talk about is in the atomic case, things are much simpler. You kind of spent more time understanding atomic case RL versus atomic phase planning. But when you go to the non-atomic case, then you are comparing PDL style planning with factored or function approximation RL. There are other kinds of interesting problems, which is if it's particularly deep RL, then the planner is learning a model which makes sense to it, but nobody outside of it. Normally, you could care less. If an AI system can survive in the wild, it's good enough. But if you want it to be quote unquote interpretable, you want to be able to understand why it is doing what it's doing, then the model it learns from pixels may not have any connection to the way you understand blocks work. So if I give it a bunch of blocks world pictures, or rather there's a blocks world like Atari simulator, where it basically takes a picture and gives a picture of the new state. And the machine basically doesn't know anything about things like on, clear, etc. It just has a bunch of pixels and it's trying to learn the abstractions, not in a purpose-driven way, but the way usually deep learning does, which is I'm just trying to minimize the error at the end. And let's see what happens. And there are many, many ways of minimizing the error. And the kinds of abstractions that your RL has learned may not make any sense whatsoever to you, the human in the loop. That doesn't mean they are bad representations. It's like, in fact, until deep learning came along, representation meant a representations that humans can understand. Knowledge representation was how humans will represent knowledge and then how they will then make the computers represent that knowledge. That it was this whole tacit explicit difference. Explicit knowledge tasks are the ones that we always look at. Right? But if you are actually learning your own representations and you have the human in the loop, then things become more interesting. There are all sorts of other issues. For example, if I'm doing symbolic models anyway, then I can give partial model of how the world works and let the RL figure out the rest of how it works. If it is only learning its own representations, then how do I advise the RL? Which is actually the paper that ICML paper that Lynn wrote that this summer, where he gives like a PDDL model, which is possibly incomplete, possibly incorrect, as the baseline to the underlying RL. And it just basically uses some parts of it. For example, it computes the landmarks and computes the options for how to get. I didn't actually talk about what options are. I'll talk about it later. Options are, you can think of them as macro operators in the context of RL. It turns out everything in RL, there is a planning terminology. There is an idea called macro operators in planning, which is a huge number of operators connected together. And an option is kind of a mini MDP. Okay. It turns out that he can actually use that to convert the symbolic model advice. The machine can use that symbolic model advice into its own terminology as needed. And so these become issues, and we'll talk about how to do some of them. But that becomes also a bigger difference between planning and RL. So that's where we will stop. I will send you the link to this talk at the first 30 minutes. Maybe you want to hear it as like a summary of what happened in the last two classes. Okay. We will end our discussion of RL and MDP by now, and then we'll act as if we understand all these distinctions the way I explained it, and then we'll start. Thank you.
It's not about us. I'm thinking. But I noticed that I was a lot better today because I reduced my line.
I also.
I'm assuming everybody who's here signed, they wanted to sign.
Yeah, don't let me forget, I need to start applications right now.
Send me a.
Okay, ask you.
That's what I do. Spent most of the class.
I need you to hold me accountable because I'm going to forget how to do things.
Yeah.